All right, welcome everybody. This is the beginning of the second session. It's going to be session 338, I believe, of the Tesos and Wi-Fi group. This session is part of the Wi-Fi design class from Wireless LAN Professionals, brought to you 100% free and like 98% in English. We'll make some Espanol there and some Russian if I can master my Russian ability. When I was in Moscow, I learned a few words. I forgot them all. I learned how to say hi and beer, and Maxim took me to a good place to eat. Is that vegetarian food, Maxim? What it was? Vegan or vegetarian?
It was
delicious. Whatever it was. It was really good. Andre, were you there with us? Who was it? It was the other Andre, right?
Alexei was with us those time.
Yeah. All right. All right, so this is the next class today. We're going to be talking about RF. We are learning about Wi-Fi. The previous class we learned about regulatory domains and the Wi-Fi Alliance and the IEEE. Three entities, three organizations that use a Wi-Fi professional, whether you are new to this field. Maybe you're moving from servers and routing and switching or security into Wi-Fi. Then you need this, and if you are a seasoned, experienced CWNE or advanced, or you do Wi-Fi every day, you still need to kind of refresh your knowledge about this. Tom, I remember you now. We talked a few times, and I send you a LinkedIn message and say, hey, I'll probably call you later and get some feedback from the conference and stuff. And yeah, we still have pending things. I see. That's how my memory works. It's
very good.
All of the suddenly it comes up, and I remember things that happen. Not like my wife that remembers everything, especially bad things I did.
So I always tell people I have a great memory. It's just very short.
Yeah. All right. So today we're going to be talking about RF, radio frequencies. Happens that all of these how we are transferring using these Wi-Fi networks and going up 6 megabits and 10 megabits and gigabits per second in the air is not data. We have to talk about the OSI model. The OSI model is not unique to Wi-Fi. This is not a Wi-Fi thing. This is a telecommunications thing. You wiring guys, cabling guys, Ethernet guys have probably learned about the OSI model. Anybody here that does not know what OSI model is? Don't be shy. If you don't know what it is, raise your hand. Okay, everybody knows what this is. Okay, then we're good. Should we just skip this? Or should we review it? Mila, what do you say? We'll let Mila choose because you guys don't give me any feedback. Do we skip this? Do we explain this?
I remember it's up to the other guys, okay?
Actually, you know what? Many people will watch this later. Go ahead, Boris.
I have another option. Let's replace it with TCP/IP stack. Okay.
That could be an option. How about you put it together and teach it to us next class? So how about, because you have to think of the guys that are coming into the field. See, that's the thing. That somebody was posting the other day on LinkedIn, or someone said like, it's so hard to find skilled people. Well, train him. That's what we're doing now. Let's provide this training. So let's just do a brief summary and kind of explain this and why. Why do we even have to talk about this in Wi-Fi? Well, it happens that, let's say I need to send a Word document. Okay? Now, this OSI model is a conceptual model. This is not how it happens, but this is a concept. Okay? That, let's say I, Fernay, will send this Word document to Tom. Okay. At the application layer, this is the document where you can see all this stuff, and then there's going to be certain formatting on that. That data, that's where you would see the bold and the tables and the center and the images of the application layer. To send that data, I will break it into chunks and then pass it on to the presentation layer, and the presentation layer will add some other headers to it and format it in a way that it can be presented to the other person. Encryption and other things happen up at this level, and then we're going to be getting those chunks of data and adding some specific information to send it. Then that gets passed down to the session layer. The session layer is going to add some more stuff to it, some other headers and information that have to do with the session, time to lives and maintaining the keep alive and all that stuff. And then that data gets passed down to layer 4. Layer 4 is the transport layer. And then in here, more headers and more stuff gets added to that chunk of data. And that chunk of data with those headers now becomes a segment. And here is where we decided we're going to send that data using TCP or using UDP. TCP is connection oriented. It's like every packet I send, data ACK, data ACK, data ACK. It gets confirmation of delivery. It's more reliable because you send it and you know you're going to get a confirmation that it was sent. Or you can send it UDP. You just send it. Data, 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 data. I don't need confirmation if you received it or not, so that's decided over here. If it's UDP data, it just goes out, and I don't need confirmation for every packet. TCP data, it needs confirmation for every packet. That segment now of the data that came from up here, plus whatever headers were added along the way, are going to be passed down to layer 3. Layer 3 is the network layer, and that segment becomes a packet. And to that packet, we're going to add IP headers, IP addresses, source IP address, destination IP address, all the IP information, Internet Protocol headers will be added to that segment, and now that segment with all the IP headers becomes a packet. So far so good? Okay. Now that packet with all those IP headers is going to get passed down to layer 2, and then that packet becomes a frame once you add layer 2 data to it. MAC addresses, source MAC address, destination MAC address. Actually, this is subdivided in 2. There is a logical link control layer, like sub-layer up above, and below there is a media access control layer, MAC. That sub-layer below, all of this MAC information gets added to that packet becomes a frame. So that frame that has data plus all the headers added in the presentation layer and the session layer and the transport layer and the network layer now have MAC headers, and it gets passed down to layer 1. Layer 1 is the physical layer. Here's where that is going to become ones and zeros. Now, those ones and zeros is what's actually going to be sent over the medium. What's the medium? Well, if you have an Ethernet NIC, actually let me get a real Ethernet NIC. Give me 1 second, be patient. Come on, for me. Mila, you're just too impatient. Okay. If you have an Ethernet NIC, those ones and zeros are going to be sent over the wire in the form of electrical pulses. It's just going to put voltages on the wire, and depending on the modulation being used, let's say 10 volts represents a 1, 5 volts represent a 0. Something like that. I don't know exactly what the real voltage is and the way it works, but it's just going to send ones and zeros using electrical pulses on the wire. If we are using fiber optics as the medium, then those ones and zeros are going to be sent in the form of light waves. If it is Wi-Fi, what we're going to be using, those ones and zeros are going to be sent using microwaves. As a matter of fact, there's going to be a transmitter. Let me just make this a different color. This guy is going to induce an electrical current on a wire. That wire is going to go to an antenna. Those electrons are going to flow back and forth really fast, and when those go up and down, then it's going to generate these electromagnetic fields going out, basically waves. Depending on the modulation, those waves are going to represent ones and zeros. So far so good? In the air is not a Word document. In the air is not data. In the air is not a segment. In the air is not a packet. In the air is not a frame. In the air is not a byte. As a matter of fact, in the air is not a bit, is not a 1, is not a 0. In the air is just waves. So, from now on, I'm going to be talking about waves a lot, because that is what those really expensive access points are sending. Waves. And that really cool, the latest and greatest phone you have, I don't know, the iPhone, whatever number it is, what's next? The 17, 18, 19? Where are we at now on iPhones? Whatever it is, it's not sending data. It's just sending waves and receiving waves. Whatever device you're using, whether it's a barcode scanner at a warehouse, maybe it is a robot in a factory, maybe it is a camera, maybe it is a computer, a phone, a tablet, a Chromebook, whatever it is sending and receiving waves. When we are designing Wi-Fi networks, we are designing devices that send waves, and then we just calculate those waves. And we're doing a survey, we are walking and measuring those waves, how much energy and what frequencies. All that stuff, waves, 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 waves. Questions up to this point. Those waves go in the air, and those waves will travel freely over free space and debilitate, attenuate, get weaker as they travel through the air. Or they may hit walls and doors and windows and people and stuff, and those waves will get weaker, they will bounce, they will go to different places. We will talk about different types of things that happen to these waves. And keep in mind, we are designing devices that send and receive waves. And the clients are devices that also send and receive waves. That make sense? Okay. Those waves will be received then by the antenna on the other end, and it's going to get the ones and the zeros. We'll talk about modulations later and see how those waves represent more or less zeros, and then I'm going to get the ones and the zeros out of that transmission. I will check, make sure that they're good. If they are good, then I will send a confirmation saying it's good. If it's bad, I just discard it and move on. And then I'm going to start decapsulating, because this process is also called encapsulation, because you are adding headers to it, basically like putting stuff in a capsule and then making it bigger by adding more stuff, and then once it goes down to layer 1 and send all the ones and zeros either in the form of electrical pulses or light waves or microwaves in the air, then those waves are going to be received by this antenna, decoded, get the ones and zeros, and then start decapsulating it and passing. Oh, is this MAC address mine? If it is for me, then I'll pass it up to the protocol stack, the IP address, and move it all the way up, and then it gets reconstructed and all of those zeros put back together at the application layer, and voila, my dear Tom, There is your Word document. I did not send you a Word document in the air. I sent waves. Does that make sense? This is how it happens. Not like they show you in the movies that there is the movie coming in the air. There is the file flying through the air. No, it's not. In the air, it's just waves. We, to better understand Wi-Fi, have to just go back to these basics. Sometimes we just get too hung up on like, oh, the controller, I'm a controller expert, and I know where to click and all this stuff. And it's like, okay, doesn't matter. What you are transferring from one device to another is just waves. You have to know how these waves work. Waves we cannot see, touch, or smell, or hear. We have to figure out how to do it and use tools that will help us understand this. Hey, Mila, perhaps you can, hook me up later, and we can also add to this party our beloved Tamograph, huh? Can do Tamosoft and use that as well?
Sure, we can show that.
Yeah, we can do that. Hey, we have plenty of time, my lady. So no worries, we'll get to it. Waves, waves, waves. That's what we're doing with these transmissions. Since it is waves we're talking about, and it's sine waves, then let's spend some time talking about waves. These waves have certain characteristics. I'm no expert in waves. I'm no expert in mathematics or trigonometry or any of this stuff, but hey, I'll do my best here to put this in simple terms, because we don't have to get hung up on the very complex mathematical equations of this stuff. That's the IEEE engineer's job. They figure out all that complicated stuff. We just have to know the basics. So let's use one wave. One of the characteristics of these waves is the amplitude. And we have to learn these terms, okay? Because Wi-Fi is like another language. We have to learn the right terms. It's not a modem. It's not a router, Tom. It's an AP. And then we talk that language. If an AP, you know exactly what I'm talking about, okay? If we talk about the amplitude, we talk about dBms, we talk about milliwatts, then we have to know this terminology. So the amplitude is basically how tall this wave is, how much energy that wave has. And in Wi-Fi we use dBms, milliwatts, or watts to refer to how much energy those waves have. When you say, oh yeah, I can see that AP at neg 45 dBm. What does that mean? It's just the amplitude of that wave. Oh no, that guy is at neg 78. Yeah, no, it's not very good. How do you know? Well, neg 78, we know it's really weak signal. We'll talk about all of that later. No worries, I will teach you how to convert back and forth. But let's just come here to the basics. Amplitude is how tall that wave is. It's like if we're talking sound waves. Volume, loud, soft. The volume will be represented by how tall that wave is. Here we're talking energy of these electromagnetic waves, and the amplitude is how tall that wave is. We good? Questions? If you have any questions, do not wait till the end when we have questions and answers. There is no questions and answers at the end. If you have questions, just stop me. Don't worry. It's like, oh, well, I had a question, but I didn't want to interrupt you. Just stop me. Say, hey, Fernay, what do you mean dBm? What's that? Whatever questions you have, go ahead. If not, we'll move on. So later you don't say like, yeah, this was a free class and we couldn't ask any questions. Go ahead, Artemio.
Yeah, hi, first time on your event. Very interesting and useful. Thank you so much.
All right, thanks for coming.
I have some problems with hearing you because you're a very passionate speaker, and when you're speaking emotionally, your level of...
You know what? Thanks for letting me know. Maybe it's this microphone here. Let me change this Zoom stuff. The audio settings sometimes go. Hang on. Let me. Oh yeah, probably let's adjust this. Okay, how about now? Is it any better?
Yes, much better.
Oh, thanks for letting me know. An hour and a half later. Should have said that like a long time ago. Hey, but it's okay.
Okay, thanks.
Okay, appreciate it. All feedback is welcome. I'm not gonna get offended or sad like, Artem, you told me I yelled too much. Okay, let's see if I have this here. Okay, amplitude. How tall that wave is. There is also frequency. Okay, frequency is how frequent are these waves going out, being sent. Frequency is like, Artemio, how about you? With what frequency do you go to the gym? That's when I ask a question and Artemio answers it.
Yeah, sorry.
That's not fair.
I didn't. It's 0 hertz.
Okay, so very low frequency.
Yeah.
Who's a gym junkie here? How about Andre? Look like a fit guy.
Nope. I have my home and my land, and that's enough.
And that's
gym for
enough
me.
to stay you
Yep.
active. Okay.
Yep.
So
3
how about
times a
then?
week.
What was that?
It was Eduardo. 3 times a week.
3 times a week. So with that frequency, you go to a gym. Okay.
Yeah.
So frequency,
Times a week.
how frequent do you do something? How frequent you say something? How frequent are these waves going out? If there is one wave, one cycle from A through B, from A through B, that's one cycle. If the frequency of these waves is one cycle in 1 second, we call that 1 Hertz. In memory of this guy, Henry Hertz, that worked on Maxwell theory stuff, and he came to this and said, yeah, if these transmissions, these waves are sent with a frequency of 1 cycle per second, that's called 1 Hertz. If waves go out with a frequency of 1,000 cycles per second, that's called 1 kilohertz. Kilo, 1,000, kilometer, 1,000 meters, kilogram, 1,000 grams. We're in America here, Tom. We don't have kilo nothing here, huh? But that's what kilo means, 1,000. So if we're talking about transmissions that send waves at 1,000 cycles in 1 second, that's called 1 kilohertz. If those waves go out at a frequency of 1 million cycles in 1 second, that's called 1 megahertz. And if those waves go at 1 billion cycles per second, now American billions, because in other places you get to 1,000 million, and then when you get to 1 million, that's when we hit 1 billion. Well, here is, if it goes at 1,000 million per second, 1 billion cycles per second, that's called 1 gigahertz, or 1 gigahertz, or how do you refer to that? Gig, jig, giga, higa? Hello, is this working? Anybody there? Giga, higa, giga, gigahertz. Okay, gigahertz. Italian giga, sono Italian gigahertz per me. Okay. In Wi-Fi, we heard 2.4 a lot. That means it's a device that is sending waves at a frequency of 2.4 billion cycles per second. There is also waves that go out at 5 billion cycles per second. That's called 5 gig, or 5 gigas, 5 gigahertz, 5 gigahertz. Not 5G, because 5G causes COVID. We had that discussion with people. You're going to put that 5G modem in my room? No, it's not 5G. Because I read on Facebook that 5G is what causes COVID. No, it's not. And I've had that discussion with people. They think that this is 5G. No, this is not 5G. That's the term that they use in cellular networks. But it's a 5G, yeah, 5 gig, okay? It's a 5 gig radio. Meaning it sends waves at 5 billion cycles per second. If now we have 6 gig, means that there are some radios that send these waves at 6 billion cycles per second. Yes, we also have 60 gig, 60 billion cycles per second. That's the frequency. In Wi-Fi, in this class, we mostly will be talking about these three. Although, as I told you earlier, I am working with Wi-Fi Halo. That's 802.11ah right now. And I have a Halo link over there. We'll be going and doing some testing in the salt flats. This is a different technology that works in the sub 1 gig spectrum. 900 megahertz in here in the US, 868 in Europe, and I don't know in other countries what frequencies they're using, but it's some 1 gig. We're gonna pay closer attention to these three, 2.4, 5, and 6. So when you see a 3 radio AP that has 2.4, 5, and 6, it has a radio that sends waves at 2.4 billion cycles per second, or 5 billion cycles per second, or 6 billion cycles per second. Is that good? Okay. Frequency. Frequency is important, and we need to understand that because low frequencies have longer waves. Higher frequencies have shorter waves. Think about it. If you have one cycle in 1 second, then you have a wave that is bigger. If you are sending waves at higher frequencies, 1,000 cycles in the same amount of time, then each wave, each cycle becomes shorter because you're putting more inside the same amount of time. Does it make sense? Higher waves, higher frequencies will have shorter long wavelengths. That's just physics. That's just how it goes. In the same amount of time, you're putting more cycles. Each wave becomes shorter. There's somebody calling him. Give me 1 second.
Fortunately, in Russia, we don't have 5G and we don't have COVID.
Of course.
You don't have 5G in Russian?
They're coming to fix my dishwasher. Like in 20 minutes, I'll pause and go let the guy in and he'll fix it. Okay, so the frequency dictates how long each cycle is. Now, why is that important? Because if you do the math to get the length of each wave, it's the speed of light divided by the frequency. You cancel some units, and then you end up in 2.4 with a wave that is about 12.5 centimeters long. That's 2.4. 5 gig, since you're putting more cycles inside the same amount of time, you end up with the wavelength that is shorter, about 6 centimeters long. And 6 gig, doing the same math, about 4.2 centimeters long, so shorter wave. And yes, 60 gig, if you do the math, is a tiny little millimeter wave, 0.4 millimeters. Yeah, it's not like precise, it just fluctuates depending on the exact frequency. But why is this important? And why are we talking about this? I came here for a Wi-Fi class. Where's the Wi-Fi design? Don't worry, we'll get to it. We have to know about this, or how are we going to design for it? How are we going to troubleshoot? And why is this important? Well, because lower frequencies have larger waves. Larger waves will go through stuff easier. And here's the other thing. Hey, Tom, I got this just for you. I know in America we don't use centimeters, we use inches. Here we go. Tom's gone. Tom's not even there anymore. Okay. Bigger waves will go through stuff easier. Shorter waves will have a harder time going through obstacles, going through stuff. Okay? If we are doing the math, let's say we have an AM radio station, we don't have very many of those left, but let's say I'm in Salt Lake City and you have a station transmitting 50,000 watts in the dial, let's say it's in the 1,000. And then you get these transmissions are tuned in the dial, they're tuned in kilohertz. So 1,000 times 1,000 is going to give you 1 million hertz. meaning a transmission that is sending waves at 1 million cycles per second. Well, if you do the math, the one we did, take the speed of light that is about 300 million meters per second. That's a long distance, huh, Don? 300 million meters per second. Give or take, it's like 299 something. And divided by the frequency, then you're going to end up with a wavelength of about 300 meters. Well, a 300 meter long wave is going to go through a tree like a hot knife through butter. And that's why AM radio stations, if you still have some, you'll notice that you'll hear radio stations from other towns. Have you noticed that? Like from really far distances. Those AM radio stations, I know they're really old, but they're still around. And those waves will go through buildings, through mountains, through stuff easily because they have really big waves. That's why we can hear them long distances. Now we move to Wi-Fi. In Wi-Fi, 2.4, now the wave is not bigger than the tree. The tree is bigger than the wave. So the 2.4 wave has to bump the tree 2.4 billion cycles per second. The 5 gig wave is going to bump the tree more times, and then it's going to get weaker because it has to hit the tree more times. And the 6 gig is even more. Then on the other side of the tree, these waves are going to be weaker if they have higher frequency because they have to bong the tree more times. They're going more cycles per second, and they're just going to get weaker. Now, people say things that are wrong. They say, oh, yeah, no, 2.4 travel farther. No, they travel the same distance. And some people say, oh, no, 2.4 travels faster. That's why, it goes to longer distance. Like, no, they all travel at the same speed, the speed of light. Okay? There's going to be a couple of things. We're going to cover more of this later, but let me just tell you right now. The waves have a size. Now we know where the size, the length, the wavelength comes from. Getting the speed of light divided by the frequency, you cancel some units and you end up with waves that are 12 centimeters or 6 inches and so on and so forth for the other ones. And then the antennas are ideally the size of the waves. So if you have a 2.4 wave that is 12 centimeters, the perfect scenario is that you have a 12 centimeter long antenna. And you can put a 12 centimeter long antenna on your iPad, no problem. But how are you going to put a 12 centimeter long antenna on your watch or on a small portable device? Then the antennas are the size of the wave or half, a eighth, a fourth, a 16, or a 32nd of the wavelength. And then they fold them. Here, let me see if I can get this guy out. They get these antennas and then they fold them and print them and put them in different forms. And here we go. That's the antenna. There's a dipole, these are old AP. But see, that's not 12 centimeters. So those are smaller. And then in other APs, in other places, I don't even know where the antenna on this guy is. See, they print them in the circuitry, and they're just small, a fraction of the waves. So the wavelengths come from getting the speed of light divided by the frequency, and then the antennas ideally are that. Well, a 6 gig antenna is smaller. Hey, where's my pen? Here we go. If you have a 2.4, it's bigger than a 5 gig, and 6 gig is even going to be smaller, a 4 centimeter antenna. Bigger antennas receive more energy than smaller antennas. That's why 2.4 is so popular. Bigger antennas, bigger waves will penetrate through stuff easier, and they will cover larger distances. Well, they cover the same distance, but you have bigger antennas. Here's the other thing. You're not cycling 6 billion cycles per second. You're only doing 2.4 billion cycles per second. So you use less battery when you're using 2.4. That's why 2.4 keeps being so popular, and manufacturers like that. And that's why IoT devices like 2.4. You put a sensor up in the ceiling or a temperature device, then it's going to send 2.4 waves, use less battery, bigger waves, will go through walls and doors and windows and stuff easier. They cover larger distances. That's just a fact. If you're designing Ekahau, in Cedar, whatever you place an access point, then the 2.4 is a big coverage area. If you give the same power to 5 gig, you have a smaller coverage area. Not because 2.4 travels farther or because it travels faster, but because the antenna apertures are different and they receive more energy. Think about it. Tom, you're in California, you like to go to the beach? Let's say you're on the beach and you have a 2 meter by 2 meter board. So it's America, we don't use meters here. Okay, it's a big board. And then comes a wave, boom, hits you. That board, 4x4 receives this energy from the wave and it pushes you away. Now let's say you cut that board and it's now 50 centimeter by 50 centimeter. You're in the same place and there comes the same wave, same energy. Is the impact you're going to receive the same, higher, or lower than before? Can you use your fingers? Higher, lower, the same?
Much lower.
Much lower. Is there less energy in the wave?
Nope.
It's the same wave, but you have a smaller area absorbing that energy. You have a bigger antenna, it's going to receive more energy than a smaller antenna. Smaller antenna is going to receive less energy. Antenna apertures, some things we have to consider. Okay. But I don't design Wi-Fi in trees, man. Okay. Say you design warehouses. No different. Think waves. Those waves are going to go through stuff. If it's a warehouse full of boxes, boxes with what? With metal cans? Or is it boxes with clothing? Or is it boxes with foam? What is it? Think waves. Bigger waves go through stuff easier and attenuate less than shorter waves. It's just physics.
Can I ask a question?
You just did. Thank you very much. Anybody else?
No, I just want to ask oh, sorry. Thank you.
Go ahead. Go ahead.
I just want to ask a question quickly, just out of curiosity. Water, when it comes to water and the 2.4 gigahertz versus let's say 5 gigahertz, would 5 gigahertz have an easier time passing through water since 2.4 gigahertz gets absorbed?
Well, they all will get scattered, but yes, it's just physics. And speaking of water, let me just show you something really quick here. And yes, we'll talk about this more later. But let me show you. Let me show you this. Where's my stuff? Hang on 1 second. Too many windows open in here.
Because that's why microwaves use 2.4 gigahertz, because that's the frequency where water really likes to absorb the waves.
They like that, huh? Here, let me show you this. Oh man, I don't remember where the...
Sorry if this is a sidetrack, so...
Oh, no. Not at all. Because, we had actually... I bring this up because I had a project. I don't know if this is it. I had a project, a successful Alta warehouse. We had a project. Oh, you know what? Let me remove the sound from this because since we're going to upload this to YouTube, they may block it because, you got music there. Okay, let me take the music out. Hang on. How do I mute this thing? Oh, right here. So there was these guys that were showing APs underwater at an Aruba show. And then I had been working with Tesos in doing some surveys in water. So I had to put the guy on one of these bags and tested doing surveys on water. Let me make this bigger here. And then I put that on a drone, and then I took it to a lake, and I flew over, and also I needed to test and see if this guy would be able to get wet, get in the water and out of the water, because we were doing design for shrimp farms. Basically lakes where they grow fish and they need Wi-Fi to have some feeders release food. And then I needed to make sure that I could survey on top of the water and see the effects, because if you have access points, those waves are going to scatter, and some will bounce off the water, some will go through the water, but it's not going to be constant what happens to it. Yes, 2.4 is going to have better chance, but it basically affects all of the waves, and we just have to think waves, and it's just physics. The effects that it's going to have on them is going to be, I don't have any documents that show what exactly happens, but it's just waves. Yes, it's going to affect it, and it's not going to travel freely in water. It's going to be affected. I don't know what scale. Maybe there are some documents out there that show that, or maybe I'll do some research on it as well. But it's just waves. I don't know if that answers your question, but yes, it has a negative, very negative effect. And depending on where the access point is in relation to the water, you're going to have better results.
Yeah,
okay.
Because I saw some research for this for Bluetooth, because of Bluetooth headphones passing the 2.4 radio passing through the head. And since we're made out of a lot of water, the head absorbs a lot of the radio waves as well. So they had to
and what did the research show?
Put the antennas at the bottom of the stem of the headphones. So keep the antenna further away from the inner parts of the ear.
Okay.
Yeah.
All right. Those waves, 12 centimeters, 6 centimeters, all those are in this radio wave spectrum that we don't see. That's why those are out of our visible space. We do have visible light waves. They are just on this little spectrum. The other ones we cannot see. And these waves, so we talk about the amplitude, the frequency, and the wavelength. Now the phase, this is not a characteristic of one wave, but a relation between multiple waves. We'll talk about this later, but in summary, waves that are in phase, they produce a gain, and waves that are transmitted and they are out of phase, they have a negative effect, either interference, it's negative effect. They destruct basically these communications. In the air, it's just waves. If you have multiple waves, you won't be able to distinguish one from the others, and then communications may be harmful unless you have things like 802.11n. That's why I got so excited with N, because now there are mechanisms that will allow you to use multiple waves going at the same time. We'll talk about this later, but phase is one of the things we'll discuss. These waves may, as you were mentioning, in the water have negative effect. If you have like metal structures, these waves may bounce and have reflections and have multipath. You have a transmitter and you have metal structures, then boom, you hit those structures and those waves bounce, and then they may get to the destination at a different time. That's what's called a delay spread. Now, for legacy devices, 802.11, 802.11a, 802.11b, 802.11g, multipath is a problem. Because let's say I'm sending these waves to Mauro. Boom! They propagate in the air. Some will get to Mauro straight. That's the green line right there on the screen. Some of those waves may bounce off of the ceiling. Boom! And get to him later in time. That's the blue line in there. And other waves, since it propagates through space, may hit the floor. Boom! And bounce off and get to him later in time. That's the orange line. So Mauro, you're a legacy device. Then you receive these waves, and then a millisecond later or a nanosecond later you get another copy of these waves, and then 2 nanoseconds later you get another copy of the wave. So you're like, I couldn't distinguish ones and zeros or who said what. So what do? Nothing. You discard that transmission. Does that make sense? That's legacy devices. That's a problem. So if you have places, factories, hospitals, things that have 802.11b networks and G networks and A networks, I know they're still out there, then multipath can be a problem. Now, if you're an 802.11n device, you have the ability that if you receive these waves and then a nanosecond later you receive a copy of the waves, and now you have the ability to give me feedback and say, Fernay, those waves you sent, I received them, and then 1 nanosecond later I receive it again, and then I got another copy 2 nanoseconds later. You give me feedback, that's a sounding frame, and then I will make the decision like, oh, we have multipath. So I can send you the letter A, letter B, and letter C and get 3 times the throughput because we have 3 ways to get to you. Or I can send you the one you received last first. And then 1 nanosecond later, at time t minus 1, I send another one. And then at t minus 2, I send another one. And then all 3 waves get to you at the same time, synchronized. So you get better signal, better SNR, better transmission. So those are decisions that N allows you to take. Legacy devices, multipath is a problem. Now, how do we know there's multipath? This is a survey made with Ceros, an AP on a stick. This is a factory. Metal everywhere. How come you have an access point? This area over here is all metal. See, the waves don't go through very well. But then around the corner, those waves look really good. What? The AP sends the wave and they just go and turn around the corner? No. There are reflections. There is metal everywhere. And if you have metal everywhere, metal on the sides, metal on the roof, metal on the floor, metal everywhere, then these APs send waves, and those waves are going to bounce and make it to different places where you don't expect it. Think waves.
Renee?
Yes, sir?
Is that reflection relatively consistent?
Yes and no. It can be from the access point it sends, and it always hits the place because the access point doesn't move. How about the client? Because it is possible that given the nature of this place, metal up, down, sideways, everywhere, then if I'm over here, I can hear that AP really good. But when I send data to that AP, where are my waves going to bounce and how is it going to get back there? Maybe it won't. Maybe from where I am, I send my waves and they bam, 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 then bounce in a different direction. It's not symmetric. So yes, this is a problem because it just waves. The AP may send waves based on its location and the antennas and all the stuff send the waves and they bam, 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 bounce and then you see them over there. But from where you are, you send your waves. I have no idea. I never heard you. And they're going to be retry. Like, that didn't work. And then you join another AP. Because maybe you were joined here and you joined me and life was good and you were walking away. And then as you were walking away, you could still hear me. But now you send me data and I cannot hear you. Then you disconnect and then you join another AP in the area. But we don't design factories, man. Well, like see, Efrain looks like in the background there are some ceiling tiles. In a lot of places, we'll see these ceiling tiles made out of metal. Do any of you have had those? Offices with metal grids in the ceiling? No different. It's not a factory, man. It's metal. It's waves. Maybe you're at a library. Oh yeah, we don't have metal here. Well, how about the shelves where you put the books? Maybe those are metal. Maybe the construction. Maybe it's drywall, pladur. Hey, gypsum carton, right? Did I say that right, my Russian friends? Gypsum carton, that what you say? See, I remember some. Correct me, come on. I probably said something wrong. Is it gypsum carton or gypsum carton?
Gipsakarton.
Gypsa. I was close. You gotta give me that.
Yeah.
Gypsa carton.
Pretty close.
That's it, pretty close. You understood, right?
Yeah, sure.
Gypsa carton. You know what that is, Alan? Drywall.
Gyproc.
What is it in French?
Gyproc.
Gyproc. Gyproc. Gyproc. Okay. And yeah, drywall will let waves go through, but what are the studs made of? Is it wood or is it metal studs? See? Think waves. If it's a warehouse, they have shelves. Made out of what? Metal, most likely. That's why when you're in a warehouse, you think waves, and then it's like, what is stored in this warehouse? Is it metal parts? Is it eggs? Is it milk? Is it fluid? We've been doing some Pepsi-Cola plants, and then I had some guys working at Coca-Cola plants too, and then they sent me pictures to the roof of Coca-Cola cans, metal, aluminum cans filled with fluid. What are waves going to go through? Tons of those. And then the next day they sent me pictures. Look, it's all empty. They came and took all the Coca-Cola cans. Then the next day, look, it's to the roof of 2-liter plastic bottles. What are waves going to do in that environment? Think waves, my friends. That's it. It's not Wi-Fi. It's not 10 gigs. It's not like it's waves. When we're designing Wi-Fi, we have to go back to these basics. Interference. I know when we hear interference, we think, oh yeah, there are microwaves and there are cameras and there's all these other Bluetooth and Zigbee and all the devices. Well, it happens in reality that most of the interference in Wi-Fi comes from Wi-Fi in the form of co-channel interference. That's APs on the same channel as other APs. Adjacent channel interference, if you have an AP on channel 36 and the next one on channel 40, those energies are going to see each other, interfere with each other, and there's also overlapping basic service set. No worries, we're going to cover all of these terms down the road later in the class. Then, yes, there are some devices that are not Wi-Fi that cause interference to Wi-Fi. But keep this in mind, most of the interference in Wi-Fi comes from Wi-Fi. Okay? That's why more APs is more Wi-Fi. Now, more APs may mean more interference. You're going to have APs in the same channel. They're going to cause interference to each other. This is what's going to happen. Okay. There are a couple of terms here. Oh, I wonder if the guys are already here. Give me 1 second. Okay. Fix the dishwasher. Guard interval. Since we're talking waves, and waves is what Wi-Fi uses to send and receive its data, then there's something called guard interval. When I'm going to send that Word file that I was sending to Tom earlier, I didn't send you a Word file. What did I send? Waves. And it's not like if I have, a 10 meg file, I'm going to send 10 megs worth of waves. No. That's not how Wi-Fi works. I'm going to have a transmit opportunity, okay? A time period. And during that time, I'm going to send you as many waves as I can. And I just don't send you waves for all that time. I send these symbols. A symbol is just 3.2 microseconds. In this case, there are other symbols. 3.2 microseconds worth of waves. And then there is a pause. 800 nanoseconds, and then I send another symbol, another 3.2 microseconds worth of waves. Is a pause kind of like when we talk. We leave a pause in between words. Or else we're going to talk about this and not even in space, we're going to know what I said. We leave a pause in between words. We just get used to talk faster, and then we can differentiate those sound waves from the other sound waves so that they don't interfere with each other. So that 800 nanosecond pause, quiet time in between symbols, groups of waves, is called the guard interval because it protects waves from the other waves. That was legacy stuff, ABG. So N, remember, my favorite one, is how can we make this Wi-Fi thing better? Well, they added that you can now hear multiple waves and group them and do MIMO stuff. And also I said, how about if when we send a symbol, instead of waiting 800 nanoseconds to send another symbol, we send a symbol and wait only 400 nanoseconds and then send another symbol, so we can send more waves faster. Shorten the guard interval to send more waves faster. That's short guard interval. Does this make sense? Now, this is one of the things we do not control. Why are we even talking about it, man? You're wasting my time. No worries. Once we start talking about MCS indexes and we start learning about those tables, short guard interval, long guard interval, it starts making sense. Also, you have to know about this because when you're designing Wi-Fi, if you have multiple waves and then you have different paths that you get, there's going to be these delays in open spaces having the short guard interval may be a problem. So devices will dynamically switch to longer guard intervals to avoid this type of problems. Because if you're in a big open space, you send your waves. Hang on one second. This for Nate.
Hi, this is Ethan again. So I've knocked at the door and no one's answered.
Okay, I'll be right there. Somebody's here at the door. So I'll be right back. But then, let me just leave this right here. Let's take a 5-minute break. I'll let the guy in. Come on. Come on. Here we go. I'll stop right here. But then, if you're in a big open space and using short guard interval, and then there might be a delay sprayed and bounces and stuff, by the time you receive the waves, they're going to be on top of each other. You won't be able to distinguish one from the other. So you have to leave a longer wait in between waves for transmissions to be successful. Okay, let's take 5 minutes. I'm going to pause the recording. Remind me of continue the recording once I come back. I'll see you in 5. Okay, yes, this may not be to scale. I know this is just to show the concept, what these things are all about. Guard interval. Okay, antennas. Let's talk about antennas because antennas are the devices actually sending and receiving these waves. So let's cover some basics about antennas. The antennas are going to have these graphs. They call them antenna charts, antenna graphs, polar charts. This is just showing in which directions the antennas are sending energy, sending these waves. There's going to be different types of antennas. The one I showed you a little bit ago, right there in the picture, is one of these guys. The antennas are printed on the motherboard. Well, on the board, and then some are in the motherboard. There are some Ruckus APs that have lots of antennas, like the ones I show you here with the Ruckus. I mean the Zeros. The Zeros guys. Notice that they have all the antennas printed and out in these modules on the outside. That's where the antenna elements are. Antennas. I got this antenna. Not this one, but it was another one many years ago that, let me just get this guy down from here. There we go. And I removed, see, a beautiful dome. Just had all this plastic and the cables and the connectors. And then I opened the antenna and inside, nothing but pieces of metal. That's it. I thought there were going to be motherboards and chips and stuff. There's nothing. Just a piece of metal with a wire soldered to it, welded to it. And that goes to a cable, goes to a connector, that connects to the AP, and that goes into a transmitter, and that's the one that injects the electrical current and makes electrons flow back and forth on these guys. So antennas are just these pieces of metal that are induced with an electrical current and generate these electromagnetic waves. That's what the antennas are. There are internal antennas, there are external antennas, as you've seen, but that's their function. They just generate these electromagnetic waves that propagate, and they are designed to propagate them in specific directions. When we talk about antennas, we talk about the gain, antenna gain, high gain, low gain. What does that mean? Well, we use, as a reference, we use an isotropic radiator. An isotropic radiator is a device that radiates energy equally in all directions, like the sun. It sends energy in all directions, and we use that as a reference, and we start there with 0 dBi. So an antenna that has 0 dBi gain basically is an antenna that sends energy equally in all directions. Well, if we start there, once we start increasing the gain of an antenna, because we talk about gain, high gain, low gain, well, how do we get there and what does that mean? If we have a device that radiates energy equally in all directions, that's an isotropic radiator, and that device has 0 dBi gain. If this, let's say, balloon with energy, we squeeze it up and down without adding energy, then where does that energy we squeeze in here goes? It goes to the sides. Now this is the area where you have gain. We'll talk about dBs later, but then 3 dBi gain, that means there is gain in this direction, but of course now it changes the coverage in this area. So this is an antenna that has gain on the sides, but then it has less on top and bottom. If we increase the gain, if we squeeze that even more, then what's going to happen is that you have less coverage up and down, but then it increases the coverage in that direction, so it increases the gain. So this is a higher gain antenna. You are not increasing power, you're just increasing the area where you are focusing this energy. That's what gain in antennas is. Those graphs, those antenna graphs, those antenna charts will tell you, one, which shape or form the radiation pattern of is, in which direction is that guy sending waves. The main lobe is the main area that the antenna is sending waves at, and then there are some side lobes and back lobes, and that is energy that bleeds to the sides or to the back of an access point. There are certain characteristics of antennas that we as Wi-Fi professionals have to be aware of, and when we are designing, we have to know which type of antennas. As Tom was saying earlier, it's like, well, depends what you need to do. Low gain, high gain is for specific environments. So let's try to explain and understand better what that means. Yes, you might be an expert when it comes to antennas and you may understand this, but bear with me because many people will be watching these videos and they have no idea, and they think that high gain is better than low gain because it sounds better. High is better than low, I think. So let's just try to explain this in simple terms so that we can better understand Wi-Fi. Antennas are going to have these graphs, the graphs specify in which direction you're sending these waves, and then there are these components. The vertical beam width is vertically how many degrees this antenna opens up to send waves in that direction. That's the vertical component. It's also called the elevation plane. Elevation, how wide is this vertically? There is also the horizontal component, or they also call that the azimuth. How many degrees does this antenna open up horizontally to send waves? So antennas have a vertical plane, a vertical component, a vertical aperture, and a horizontal component, an azimuth. How many degrees this antenna opens up horizontally? Questions up to this point. Okay. Now, if we, for instance, like in this graph over here, we have one of these dipole antennas, like this. The elevation plane is, if you're looking at that antenna from the side, is vertically how many degrees that antenna covers. Okay? The azimuth, the horizontal, is if you're looking at the antenna from the top, like this. Then horizontally, where does this antenna cover? Where does this antenna send energy? Where does this antenna send waves? Vertical component, horizontal component. That make sense? Okay. There are three main types of antennas that we talk about. We talk about omnidirectional antennas. That's the one on top that is like a donut. And when it says omni, omni means all. Omni-powerful, omnipresent. Omni means all. Of course, it's not an omni-omni, because omni would be what? An isotropical radiator, that it sends energy in all directions. Omni is short for omnidirectional in the horizontal plane. Any antenna that is omni, it covers 360 degrees around it. This AP is an omnidirectional access point. If I mount it like this, it's like a donut. See one on top? It covers 360 degrees around it. And then the energy, as you can see, is like weak in here. And sometimes they say, my Wi-Fi is really low. I don't know why, because I'm right under the access point. Maybe you are in the hole of the donut. And then over there, the signal is not very good, because this guy can have a pattern kind of like this. Okay? Omnidirectional in the horizontal plane. Then there are some semi-directional antennas that they, instead of covering 360 degrees, they're going to cover just like, let's say, 90 degrees or 120 degrees or 30 degrees. And then they are focusing the energy in a more specific place. Not just everywhere, just in a specific place. And then there are the highly directional antennas, kind of like the plate I have over there. Those have a really narrow beam width, and then they go at 5 degrees, 7 degrees, just a smaller beam width. But that's what allows these point-to-point connections to go 20, 30 kilometers on a point-to-point link, because you're focusing the energy on a small area, and then you aim it straight at the other one, and then you can establish these point-to-point links at long distances by focusing the energy. So we have this omnidirectional antenna, and we have a low gain, means compared to an isotropic radiator, I'm just squeezing that a little bit. If I have a higher gain omnidirectional antenna, what those graphs are going to look like is going to be this for the low gain and that for the high gain. Meaning, if you squeeze it more, top and bottom, the energy starts increasing in this direction. Now you can cover a longer distance that way. Basically, you have a donut, and if you flatten it more, now you have a pancake. And if you flatten it even more, now you have a tortilla or a crepe. And it's bigger this way, but it's really, really skinny, instead of a fatter, smaller donut. Does that make sense? Same amount of mass, you just send it in different directions. Toys R Us, you know that, the toy store? They had a problem at a warehouse. Well, now they have a bigger problem. They shut down all the stores. But years ago, they had a problem at a warehouse. And then the Wi-Fi was low. The scanners didn't work quite well. So they got these high gain antennas. And now the scanners didn't work at all. They had to go like to the very end of the building to get signal. It's a stupid thing, you know, it's just not working. We got this really expensive high gain antenna. It doesn't work. So they got the guy to troubleshoot. So like, wait, why did you buy high gain antennas? Oh, because, you know, high gain is better than low gain, isn't it? And they were more expensive. So we assume that high gain, more expensive, that they were better antennas. But evidently, it's not working. So the guy gets up there on a forklift, and then they swap the antennas and put some of those really cheap, you know, blue dot, white dot type of antennas, low gain. And then as they were replacing the antennas, a guy drives by on a forklift and said, whatever you did to the Wi-Fi, it works now. The IT guys were like, how do you put that cheap low gain antenna and it works? And our expensive high gain antennas don't work. Like, it's not if it's high gain or low gain. What do you need it for? Well, I need a cover down here. You get this high gain omnidirectional antenna and you put it up on top of the racks in the warehouse. You have great coverage up there, but not down there. The rule for the antennas in Wi-Fi design is very simple. Get the antenna that covers what you want and does not cover what you don't want to cover. Again, in Wi-Fi, get the antennas that cover what you want to cover and that does not cover what you don't want to cover. We'll talk about this in a little bit. Antennas send and receive waves. Let's explain gain in a different way. Using light. Something that we... Oh, hang on. I got a LinkedIn invite from Artemio. Here, let me accept that. And Omran. And Srinivasara Marao. Oh, man. Okay, I'll accept it. Okay, let me share my... Let me stop sharing this guy. And let me start sharing my phone. Okay. My phone on your screen? Okay, pardon the mess. Okay. Yeah, this is my Halo stuff I'm working on, but I'll show you that later. Okay, let's talk about gain. Ooh, dark. You're not afraid of the dark, are you? Okay, watch this. It's kind of have a flashlight over here. Let's say this is an antenna. This guy has a vertical component. This will be the vertical plane. Okay, how many degrees did this open up vertically? This also has a horizontal component. How many degrees this guy opens horizontally to cover that area? Vertical plane, horizontal plane. We good? Okay, let's say this is a low gain one. Let's increase the gain on this light. Ready? Here we go. I'm going to increase the gain. Wow, man, look how bright it is. Did I increase the amount of batteries I have or the amount of light? No. How is it brighter then? Because I'm focusing the light in not a bigger area but a smaller area. Now what changed? I have a smaller vertical plane and I have a smaller horizontal plane. I just increased the gain of this light. That's the same with an antenna. You increase the gain of an antenna, you are focusing the light, the area where you're sending energy, the area where you're sending waves to just that area. That's the main area. Does it make sense? Hello? Yes? Okay, good.
Yep.
So now I can go to specific places and make this brighter in that specific place without covering a whole bunch of other area. I just need a cover there, okay? There you have it. Same thing if I just put it, like if we're doing directional antennas on a warehouse, and I just want to cover this area, then I use a directional antenna here. Or an auditorium, a lecture hall at a university. Then you just cover this area here. And then you put another one there. And then you put another one there, and they don't see each other, they're not causing interference to each other. If I have omnis and they cover a larger space, then you're going to have more interference. Low gain, high gain. Low gain, high gain. Same thing for any antenna. You're just focusing the energy on a more specific area. Not by adding power, is by design. The antennas are designed to cover a specific area. Low gain or high gain is not something. See, this is another misconception. You know, let me, before I leave, there's an application called Theodolite that allows you, when we're doing design, this is extremely helpful. Like if I'm at a warehouse and I want to put the APs in certain area, I can see where they cover. If I change this from 1 to 2, this is what the human eye sees, okay? Then if I go back, let's just leave it here so we can better see. Then this gives me how many degrees. Look to the right where it says 10 degrees, minus 10, minus 7, minus 6. Can you see there? Somebody give me feedback so that I know you're following me.
Yeah.
Okay, see where it says minus 30? Then that means that from the horizon, that antenna is tilted 30 degrees down. Okay, that's like right here. This is minus 20, minus 15. If I look at this access point, notice that it has the number of degrees, and I tilted that guy down 30 degrees. Because this guy is a semi-directional one, and I need it to cover a specific area over here. This, for point-to-points, is really useful, because if I want to do a point-to-point, let's say, let me know if the sound's still working. I want to walk away and lose sound.
Yeah, it's okay.
If I want to put an antenna, let's say, aiming there, then now notice that here it says that it's a 15-degree up, meaning the antenna has to be aimed 15-degree up. And if I'm on the and I'm shooting down, then it's going to tell me how many degrees I have to aim down that antenna to get there. This application is not very expensive. It also, if I go to map, it gives me, like if I want to run a point-to-point from the roof of my house to that shopping mall over there, it shows me that I'll have to aim it, and if I'm aiming in this direction, I will be getting to the roof over there by that dark circle. Also, I can take screenshots of these. I can send, see up where it says email, where it says mail, upper right corner over here. Then I can send an email with all the coordinates, altitude and GPS and all the information about this location. And you can use this in your documentation. You just take a screenshot of this and add it to the installers and say, hey, you know, like over there is where I want the antennas, and then add all of this additional information. Now let me stop sharing over here. Turn this light back on. Questions up to this point about antennas?
What was the name of that application?
Theodolite. 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 Okay, let me come back over here. I think it was called Dioptra on Android, but I don't know if they're still around. All right, semi-directional antennas, then it's just an antenna that covers a more specific area. 30 degrees by 30, 60 by 90, 90 by 60. They are just different. Now you know what the vertical component, vertical plane, or horizontal plane are all about. And then there's the highly directional ones used for point-to-points, and they have like 3-degree, 5-degree apertures. That's where you're sending the energy, and that's what those graphs, those polar charts mean. Here we go. Hando just put it there. Oh, theodolite. Here we go. Thanks for fixing that. This is in one of those plants. If you have an omnidirectional antenna and you need to cover this area, then that omni right there is going to cover that area, what you want, but also, no, that should work on Android as well. GPS, geo camera, Android also, I think the Optra used to be on Android. I don't know if that's still the name. But then you're covering areas you don't want. You don't want to cover out there. So in that case, you'll just use a semi-directional, like here, shooting for the area you want, without covering areas you don't want. What's the deal with that? If you have an antenna that is covering areas you don't want, in Wi-Fi, antennas will transmit waves only when there are no other waves in the air. So if I hear over there, I will not talk. So we'll get to another one, and I'll explain this in a little bit. Let me just tell you about Costco. Costco, for those of you who don't know what Costco is a place where you go buy a whole bunch of stuff you don't need. It's horrible. Okay? But it's a place where, hey, they have access points too. This is the dairy section where they have a fridge with cold stuff inside. Notice in here, on the outside, there is the access point. On the inside, there's the antenna. Why don't they just put the access point inside? Well, you know, it's a fridge. It's cold. The access points will have active components. Motherboards, chipsets, CPUs, memory, RAM, all that stuff that needs to be within certain temperature levels.
Or just use outdoor antenna, specific outdoor antenna inside the fridge.
They use specific ones because this one is a semi-directional just to cover that area. And remember, the antenna, there's nothing in it, just metal, pieces of metal, so they can withstand temperatures, higher temperatures, lower temperatures, better than the access point. I mean, you could get a cold temperature rated access point that is going to be more expensive with a special enclosure and stuff, but in this case, this works just great. Same as in, let's say you need to design at a beach. There is sand, there is water, there is wind, there is all kind of high temperatures and rain and all the stuff. Then you can put the access point on the inside of the building and then put an antenna on the outside of the building. So the opposite of this. AP inside, antenna outside. That's use of external antennas. External means that it is external to the access point. Kind of like this guy over here. I just stop sharing for a second. See this guy? This is a warehouse antenna. It's like 120 vertical by 15 degrees horizontal. So 120 degrees here and only 15 degrees horizontal. Put it in a warehouse, it lights up a whole aisle. Here's the access point, connectors, cables, and antenna. This is an external antenna. You have the access point, then you can direct this in whatever direction you need it to cover. Okay? Some people may say, like, well, but that's more expensive. Yes, but hey, whatever you need to cover. Antennas are those beautiful devices that allow us to send waves in a specific area. Look at this guy. Ooh, that looks like the one I just showed you. Notice that. There's the access point. There's the directional antenna. What's wrong with that picture? Because I was doing a survey and they said, yeah, Wi-Fi here is really bad. They have a directional. They
They're
have a
omnidirectional.
directional antenna, you're right, and they're aiming at the roof. Where do I need the waves? Down where people are sitting, down here. The antenna is aiming at the roof. So the semi-directional antenna, it's covering what I don't want to cover. I told the guys, you have to tilt them 45 degrees down. That's why this guy is kind of like aiming down, because it's semi-directional and it's shooting in that direction over there. If I aim it up, now this guy's shooting waves up there. Think waves. We good? Does that make sense? So how close is too close when it comes to placing access points in whatever they are, in the ceiling, in the roof, whatever they are? Well, as you can see in these pictures right here, they probably mounted them too close. There's always a reason why. I know we can make fun of how these APs are installed, but we never know why they mounted them that way. Sometimes they're doing upgrades. I've seen places where they say, oh, no, the Ruckus AP, that belongs to the other company that lives here. The Cisco AP, that's our AP. We just have collocated spaces, so we have multiple vendors in here, and everybody just places their APs up there. Maybe the other one, they didn't have the brackets to mount the APs properly, so everybody's got a reason for it. I mean, nobody's going to do this on purpose knowing that it's not a good idea. When they are too close to each other, even if they are on separate channels, like channel 36 on one AP and channel 165 on another AP, the fact that they're so physically so close to one another will cause near field RF problems. Around those antennas, those radios, there's going to be these magnetic fields that regardless of which channel you're in, which frequency, that energy is going to affect that energy. So you want to keep them separated. So there's a song called that, keep them separated. Those APs, try to keep them as away from other APs as possible. I know in many places they just put in one right next to the other. Not a good idea. Try to keep those separated. When you are installing Wi-Fi and designing Wi-Fi, you got to keep these things in mind. Sometimes they are migrating, and then the old one's still up, the new one's still coming up, and they both are working at the same time. Hopefully, it's just one or the other. Whatever reason it is, just keep those things in mind. This access point right here, all the way up, is an omnidirectional one. Well, I don't have one just like that, a Cisco. Actually, I have a Cisco AP in here. Watch this. That's a Cisco AP that is designed to be mounted in the ceiling like that, but it's mounted like that, up above the ceiling. That's in the Charles de Gaulle Airport in Paris, that they mounted them like that because they were told to do so. And I actually met the guy who worked there at one point and said, why did you guys mount the APs like that? And say, hey, the owner building said, like, that's how you mount the APs, and if you don't want to do it, we'll hire somebody else to do it. Say, okay, we're going to mount them like you say, master, but you just have to know how antennas work and that they are sending waves. So basically, in there, if this access point is to be designed to be mounted in the ceiling and it has an omnidirectional pattern, like a donut, and you mount it in the wall or above the wall like that, like in the picture, then you turn that donut into a wagon wheel. Now you have those waves that were going horizontally here. Now they're going to be going up and over and there and down like a wheel. So now the donut just turned into a wheel. You have to know how antennas work and what they're doing and their patterns so that you know how to mount them. And yes, we're always so worried about the access points and how are the access points mounted. Well, yeah, they have to be mounted properly, or else we're going to have antennas like in that convention center aiming at the roof, or APs mounted close to each other. Yeah, that's important. But remember, antennas exist not only on the access points. Devices, phones, computers, tablets, they all have antennas. They're just radios that need to send waves and receive waves. So Let's talk about the antennas on the client side. Who's the client? Yes, we always think, oh, it's a phone, it's a tablet, it's a barcode scanner. Well, how about if the client is that yellow truck right there? Notice that I put that white truck behind it, just to give you an idea of the size of this Wi-Fi client. And up there at the very top, that's where the antenna is. So, where is the antenna on the client in relation to the antenna on the access point? They both are sending and receiving waves. The AP is sending waves to the client. The client is sending waves back to the AP. Where is the AP? Oh, this thing frozen. There we go. There we go. Where is the AP? So, hang on, there is something going on with this thing that doesn't seem to be working very well. Okay, here we go. So where are the antennas on the clients? Where are the antennas on the APs? Yes, the client can be a phone. How about a phone being held by a football fan or a soccer fan at a stadium? They're sitting, and then where are the access points? In this stadium, the access points are those little white dots on the background. I don't know if you can see them very well, but there's no roof to put APs everywhere. There's no ceiling. So where they put the APs? Under the seats. And yes, I did the survey over here. One AP, any AP, you can see it everywhere in the stadium, like everywhere. So I said, well, when it's game night, and they say, why? I said, because I want to come and do a survey when there is a game, and the seats are full of people. People also attenuate these Wi-Fi waves. Attenuation is another word for weakening of the signal. So one AP that used to cover the entire stadium when the stadium was empty only covers a smaller section when the stadium is full. Yes, that's expected, and when you're designing Wi-Fi for these high-density places, keep that in mind, because now that AP that covered the entire place only covers a smaller. That's what we're trying to do. Other places of high density, these auditoriums. In here, even though there is a roof, the ceiling is made out of screens, video screens. So there's like no place to mount APs out there. So where do they go? Under the seats, in those boxes. That is where the antennas and the access points will go to provide waves for the people near them. Now, this is at a hospital. This is a client where the antennas on the computer are inside that metal box. See, keyboard here, that box is where the computer and the antenna is. How are the access points going to send waves to these clients? How are these clients going to send waves back to the APs? Maybe the APs are high and the clients have antennas up high. That's good. That's expected. But what if the antennas are down low? Because these robots, they have the antennas here like 5-10 centimeters from the ground inside the robot. In this place, the guys ended up putting the access points under that floor right there, because that's where you need coverage. That's where you need waves. Waves going from the APs to the clients, from the clients to the APs. Then bring the access points as close to the customers, to the clients as possible. And I know when we think customers, when we think clients, we usually think a human holding a device. Well, yeah, we've seen several here in the last few pictures where the client is not a human. It's a robot. It's a device. It's a truck. It's a vehicle. It's something that needs to send waves and receive waves successfully. What's the rule for the antennas? Get the antenna that covers what you want without covering what you don't want to cover, and move the APs as close to the clients as possible. The closer you are, the better results you're going to have. Now, when we talk about antennas, we have all these things to worry about. Now, there are terms. Remember, Wi-Fi is like a second language. We have to know the terminology. Now we talk about gains in the antennas. That's another thing we don't talk on a daily basis. This is specific to what we do. Gain of the antennas. Beam widths. There is the vertical component, the vertical plane, or the horizontal component, the horizontal plane. Polarization. Yeah, there are vertically polarized antennas, horizontally polarized antennas. There's the cost. Once you have these in external antennas, let me just bring this guy over here. You have external antennas and cables and connectors and access points. Yeah, it costs more money. Cost is one of the things you have to consider when you're doing all of these designs. And people say, oh, no, those antennas are too expensive. Let's just get omnidirectional ones. Okay, but we're not going to have the same results, because if we have a high density place, you want to beam those waves, that energy, focus it on a specific place so you can reuse those channels somewhere else and they don't see each other, and reduce the amount of interference. Had a warehouse where they say, like, we need 2 APs in every aisle because we need redundancy. Okay. Presented the proposal, I said, oh, no, that's too much. We need less APs. Okay, then we're not going to have 2 signals in every hallway, only 1. No, but we need redundancy. We need 2. Okay, if I put 2, you say it's too much, too many APs, too much money, then you're going to reduce the number of APs, then you're not going to have redundancy. Pick one. You can have redundancy, 2 APs per aisle, or you can save money. So that's how it goes. You have to know the cost of doing a good design. What are they used for? Are they going to be indoors, outdoors? Are they going to be up high? Are the clients going to be down low? Manufactured. There are some access points that will take certain external antennas, but depending on the manufacturer of choice, they may say, like, oh, you have to buy antennas from us. Because if you don't, then you're going to lose the warranty or you lose support. So just know that the manufacturer you choose for the antennas may, I don't know, maybe void your support contract. So just beware which type of antennas and which type of connectors. There's N-type connectors, there's BNC connectors, there is RPSMA connectors. There's all kind of connectors, and you have to make sure that you have the right connectors for it. Now it's more work because you have to install the antenna and the bracket, and you have to mount the AP and the cables and the connectors and make sure that they are twisted correctly, that they are installed properly. All those things have to be talked about when you're doing design, and see which type of antennas. There are some antennas with leads for 2, 4, and 5. There are also for 6 gig. There's all kind of different connectors. All of those now part of the consideration. What's the main load where you're going to be sending that, and how much energy is bleeding on the side or on the back of those antennas. This is a project where we did a survey for an institution, and then when we were on site, I asked, we were on the 4th floor of this building, and I asked about these apartments over here. And I said, who lives over there? I was here on the 4th floor. The guy said, oh yeah, don't worry about it, that's not us. It's like, no, I worry about it because we are by the window. You have a Cisco access point near the window. This guy's not sending Wi-Fi, he's sending waves. And those waves are going to go through the single pane glass, over the security area, into those apartments, and anybody with a cheap Wi-Fi device can get those waves, get the ones and zeros out of them, and decipher a lot of your information. No, this is just configured just for us. I got arrested that day because I was doing a survey that night, and cops came, took me away, took my sidekick, took my computer, and I was just doing a survey. So, well, you need permission from the something security officer. Then I could explain what I was doing, they let me go, and then the next day I showed them. I was like, see, I could see from 100 meters over there by those apartments, I could see the SSIDs, the type of access points you're using, the channels, the security, the cipher, all of that stuff can be really, really easily decoded, and anybody can do discovery of your networks like that. You have those APs by the window sending waves. Anybody out there, 100 meters, there's no obstacles or trees or anything, just open. Anybody can see those waves, and if they have enough time and enough interest, they're going to gather enough data and make a discovery of your property, of your customer, of your client, or your network. Maybe it is your network that you're protecting. Move those APs away from the windows unless you need them. I don't want to cover those areas because I don't want to cover what I don't need. You don't need coverage over there. If you need coverage over here, yes, this guy covers over here, but it's also, since it's omnidirectional one, it also covers all the way out there where they don't need it. You don't need it over there. And this is bidirectional. Wherever you send waves, you also hear waves. So just think that you have a hearing aid that allows you to hear 5 kilometers around you. But, I mean, how does that sound? It sounds great. I can hear everything. If somebody's talking bad things about me, I can hear it. But you can only talk when you don't hear anybody. So, yeah, if you put an access point here and it's on the same channel as the APs on those towers and I can hear them, I will only send waves when I don't hear anybody. And if I hear, I send my waves. Oh, I have to send more. I have to wait and make sure and listen, and if I don't hear anybody, I can transmit. So you don't want to cover areas that you don't need to cover. Remember, that's the rule for the antennas. Get the APs that cover what you want without covering what you don't want. All right, my friends. My friends from Sweden, from Norway, from Brazil, from Argentina, from the US, from Saudi Arabia, from Russia, we have people from all over the place. Thank you very much for coming. I think this is the end of session 338 of Tesos and Wi-Fi. Remember, we haven't done 338 classes. This is the second class of this free class that Wireless LAN Professionals is bringing to you. Is a Wi-Fi design class that applies to designing Wi-Fi networks with any tool of choice. Ekahau, Hamina, CDOS, Wavelify, Tomograph, all of these basics we need to know so that we can design better Wi-Fi networks. Yes, we're going to be covering every single topic we need to cover in design. There's no rush. We'll take our time and cover every topic, answer every one of your questions, and share knowledge. That's what we do. And this time, for free! You're not paying a dime, and this is free. And remember, if you don't like the class, we'll give you a full refund. That guarantee you get. Free love for everybody and free training for everyone, regardless or where you are connected from. Maybe you're not here today. You're watching this, I don't know, tomorrow or another day. This is going to be recorded and uploaded so that you can also have access to this valuable training that is going to help you in your career. Whether you're learning from scratch or you are already trained, this will help you have better understanding of how these technologies work. Thank you very much. I'll send you the invite for the next session for tomorrow. Have a good night. Thank you for coming.